Okay, then welcome everybody to the weekly colloquium of the Physics Institute of the UNAM in Cuernavaca, Mexico. Our guest today is Dr. Stephen Power from the Dublin City University in Ireland. And let me say some few words on his vitae. Dr. Power received his PhD in 2012 from Trinity College in Dublin under the supervision of Professor Mauro Ferreira. And his PhD research was focused on RKKY interactions between magnetic impurities in graphene. Following this, he undertook postdoctoral fellowships under Professor Antti-Pekka Jauho at the DTU in Denmark and Professor Stefan Roche at the ICN2 in Barcelona. He returned to Trinity College Dublin in 2018 with a starting laureate grant from the Irish Research Council, and in September of 2021, he began as an assistant professor in Dublin City University. His recent research looks at the interplay between electronic, spin, and valley properties in 2D systems. He is particularly interested in how nanoscale patterning, strain, gates, perforations, or substrates can influence these properties. Yeah, Stephen, thank you very much for joining us today, at least virtually. It would be a pleasure to have you here in Mexico in person. And yeah, we're looking forward to your talk.
Great. Thank you very much, Thomas, and thanks for the nice introduction. It's a pleasure to be here and to talk about some of my recent and some of my not so recent research. So kind of the main topics Thomas mentioned are what I'm going to be talking about: valley, spin, and their interplay with essentially with electronic charge in graphene and graphene-based nanostructures. So a brief overview of the talk. I'm going to give a very quick introduction to the concept of valleys in graphene and how these can be manipulated by strain, because this was my first approach or my first introduction to this topic. The meat of the talk is probably going to be this second topic, which looks at an alternative approach to manipulating valley behavior in monolayer and bilayer graphene, by playing around with gaps introduced by mass terms or interlayer biases. The last two sections are both new and unpublished work. I'm going to talk about edge magnetism in graphene flakes and how we can use machine learning approaches to help us here. And finally, I'm going to talk about proximity spin-orbit coupling in graphene when it's coupled to transition metal dichalcogenides, and talk a little bit about how this can be tuned by engineering the geometries. So to begin, let's talk a little bit about the basics. So what do I mean when I say valley? Essentially, at low energies, the electrons in graphene can sit in one of two cones or valleys in reciprocal space. And we dub these the K and K prime valley. So this is a new degree of freedom that low energy electrons in graphene can have. The aim of valleytronics is to try and exploit this new degree of freedom and use it to store, manipulate, or transmit information, somewhat analogous to how you would exploit spin in spintronics. An issue here, because valleys aren't magnetic, you can't play with them necessarily easily with a magnetic field, is how do you separate electrons that are in the K or the K prime valleys? How do you create polarized currents? How do you detect these, and so on? So these are some of the issues I'm going to talk about today. So my first introduction to how you could play around with this valley degree of freedom was by using strain. So essentially, when we're modeling graphene, we can introduce strain in a few ways. It affects the electronic properties in our tight binding type models because it varies the lengths of the bonds. So it varies these hopping probabilities, which depend on the lengths of those bonds. And this will depend on how we strain the system and how the bond lengths change. In Dirac or effective models, this modulation of the hoppings can be written in terms of a gauge field. So that's this A term here, which in turn is written in terms of the components of the strain tensor. As we have a gauge field, this is somewhat similar to how a gauge field appears in electrodynamics. And if this gauge field, this vector potential here, has a non-vanishing curl, we can associate with it a pseudomagnetic field, which appears mathematically similar to how a real magnetic field would appear in these equations, with one small subtlety. that pseudomagnetic field and the vector potential defining it takes the opposite sign in the K and the K prime values. So this is to maintain overall time reversal symmetry, which can be broken by a real magnetic field. But of course, if we're simply applying strain, we're not breaking time reversal symmetry. So within one valley, it looks like time reversal symmetry is broken, but when we consider both valleys together, it's restored again. And our work in this area was motivated by some early experiments that looked at creating strain, creating small bubbles or blisters and combining them to kind of make custom heterostructures, and also by some possibilities that were suggested by experiment of deliberately patterning strains, maybe by engineering substrates or these kind of pillars and placing graphene on it and kind of maybe engineering these strained structures. So how does valley come in here? Whoops, am I missing a slide? No, but because the pseudomagnetic field takes opposite signs and opposite valleys, if we could engineer a pseudomagnetic field structure, the Lorentz force experienced by electrons will be opposite, and you would expect electrons to travel in different directions. And this is what we found could happen with some simple bubble structures. We found that depending on the geometric symmetry of the bubble, we could design different types of devices. If a bubble was circularly symmetric, the resultant pseudomagnetic field, shown here in purple and green, would have this threefold structure, and the expected vortices that formed would be different for each valley. So if an electron's coming in from the left, if it's in the K valley, it's going to be repelled because the vortices here are going against its direction of travel, where it will be funneled through the bubble if we're in this red K prime valley, simply because the vortices align with the direction of the incoming current, and it can wind its way through. So this held up not just kind of schematically, but when we did full calculations and kind of mapped the valley dependence of the current that passed through, see that the current passing through the bubble is indeed mostly polarized to one valley, whereas the other valley is kind of scattered in a wide region outside this. So this type of geometry bubble could act very much as a valley filter, that if we have both valleys coming in, one is going to be repelled and we'll only get one valley through. So this might be a nice valleytronic component. Another symmetry bubble, if we consider a triangular symmetry, so not circularly symmetric, but instead triangular, this type of structure creates a largely constant pseudomagnetic field. So in this case, we would expect the deflection direction to depend on the valley. So roughly the same for each valley, but with opposite directions. So approximately the K valley here would experience a Lorentz force in this direction, and K prime in that direction. And again, if we do the full tight binding calculation and look at the valley polarization, this is the behavior we found. Incoming electrons largely a combination of both, but the outgoing were scattered at wide angles and with an angle that depended very strongly on the valley they were in. So this type of bubble, you can be seen as maybe a template for a valley splitting device. So there's a nice range of possibilities that have really been published since in both experiment and theory. And two recent enough ones show that the type of geometries I'm considering here, both circularly symmetric and triaxial or triangularly strained bubbles, are now very feasible experimentally, grown on different substrates or created with, I think in the former case here with an AFM tip, with experimental parameterization allowing control of the width of the bubble, the height of the bubble, and so on. And again, some of the features that you would expect from pseudomagnetic fields, such as Landau levels, pseudo-Landau levels, also being detectable. There's also been a really nice range of theoretical works in this field, kind of going far beyond our simple devices, looking at these in combination, combining these to create more advanced structures, or including various degrees of modeling, taking into account relaxations and how these affect it and so on. So it's quite a nice field, but one of, I guess, the limitations that we saw in bubbles is that some of this behavior wasn't extremely robust. It could be affected by slight changes in the energy or the size. It would be hard maybe to control some of these features in experiment. Although, as I said, experiment has come on a lot in a few years since. So we started to think of other ways that perhaps this valley degree of freedom could be controlled. And one way that has been suggested is through mass engineering. So let's talk about a little bit about what we mean by mass engineering. Essentially, a mass term in graphene is related to a bandgap opening, and it's related to breaking the sublattice symmetry in graphene. So if we have a standard hexagonal lattice of carbon atoms, if all these atoms are equivalent, we have a zero mass term. But if we break the equivalence of atoms onto different sublattices, for example, by changing the potential so that atoms on the A sublattice experience a potential VA, and atoms on the B sublattice experience a potential VB, then we have a non-zero mass term. And if we see how this changes the band structure, we go from this massless, gapless Dirac structure to a gapped, massive Dirac picture. So we can control a band gap by breaking sublattice symmetry. And this can be realized in a few ways. Some of these are by placing, for example, graphene on boron nitride, that in, at least locally, some of the carbon atoms will sit over boron, experiencing one potential, some will sit over nitrogen, experiencing another, breaking the sublattice symmetry. Another possibility is sublattice asymmetric doping. And this has been achieved in CVD-grown nitrogenated graphene, where depending on the conditions, you can find that a majority of the impurities are on one sublattice in one region and another sublattice in another region. So you can create these large domains with a sublattice-dependent doping, which should induce that the average potential felt by electrons is sublattice-dependent and should induce a gap. So how can this affect a valley? So in gapped graphene with a finite mass term, there's also a finite Berry curvature, and this Berry curvature depends on the mass term. Furthermore, if you do a semi-classical analysis, you see that the Berry curvature term will give rise to an anomalous velocity. And the direction of this term will follow the valley. So you get this, an electron traveling in this region should experience a valley-dependent deflection. So this additional term here, due to the finite Berry curvature, will deflect one valley in one direction and one valley in the other. So how can we exploit this? This has been predicted to give rise to a valley Hall conductivity, a quantized valley Hall conductivity inside the bandgap, as shown here. So this you can see from analytic methods, but also by following, for example, Kubo-Bastin simulations of large-scale systems and extracting it in that way. Again, you see this quantized value here of the valley Hall effect, which is caused by different valleys going in different directions, compared to the overall Hall signal, where the individual valley contributions cancel each other out, and you get no Hall conductivity. So this is great. There's a potential way to split valleys using mass terms. How do we look at this in experiment? How do we detect this effect? So the main tool here typically is non-local experiments, in particular non-local resistance experiments, like this famous example a few years ago, almost a decade ago now, from the Manchester group. And the main idea behind these experiments is to use electrical measurements, standard electrical measurements, to detect more exotic phenomena such as valley or spin Hall effects. The idea being here that you drive a current between the two local probes, in this case 4 and 8, and if a valley or spin Hall effect is present, you will get a splitting here into different directions. This creates a non-local signal which permeates throughout the system, and at a distant set of probes to an inverse spin or valley Hall mechanism, this creates a measurable electronic current or a voltage that can be measured. Again, the idea being here is that you're using electric measurements to detect more exotic spin or valley Hall effects. So it is indirect. And generally what you're looking for is an enhancement of this non-local signal compared to what would happen maybe in just a purely ohmic or simple case. And that's what the curves here show. So the non-local resistance, I think, is the red curve here. And there's a large peak in it here, which is typically associated with some sort of underlying Hall mechanism that's creating a long-range current, that's propagating throughout the system and creating a measurable voltage elsewhere. So there's a large peak in the non-local resistance in a similar energy range to what you would expect for this Valley-Hall conductivity term, which peaks in the gap of the system. So the interpretation here for this type of experiment is typically that this encapsulation of the system in boron nitride induces an effective mass term in the graphene layer. So this local sublattice symmetry induces an effective mass term. This in turn induces a Valley-Hall effect at the local probes and an inverse Valley-Hall effect further away. This is driven by the Berry curvature mechanism I mentioned. So we create long-ranged, non-local Valley currents. And the typical idea is here, because we're in the gap, we shouldn't have Fermi surface conduction. So the argument used is that these currents are in fact mediated by persistent currents. So by currents in the Fermi sea beneath the gap of the system. So I guess the question is, can we reconcile this? Do we have a consistent theory going from our Berry curvature mechanism to measurements in experiment? And typically what we would do if we have this sort of semi-classical or analytic model and a transport simulation is a transport experiment, is that we would perform quantum transport simulations and try and reproduce the results of the experiments and link these then to the underlying theory. However, there are complications if you try to do this. It's very difficult to reconcile the valley splitting mechanism, this Berry curvature effect, with simulations of transport experiments. If you do this type of Landau-Boddicker multi-terminal simulation, you can find a finite non-local peak, but only for very short devices, for devices with certain aspect ratios very, very different to the experimental systems. And in these cases, the physics that you would find in your simulations are driven by Fermi surface contributions. So if you're in a gap, these are going to be evanescently suppressed and vanish very, very quickly at length scales much lower than the experimental systems. The other thing these simulations tend to find is that these currents are highly sensitive to edge geometry. The type of behavior you see depends on certain types of edges, which is not consistent with the experiment, who finds results without playing particularly, which don't have a particular mechanism to control the edges. So they don't know what edges they have. It's unlikely they're going to have perfect edges that will give the type of states predicted by theory. So there's a bit of a problem here. And one of the other issues is that the proposed mechanism is based on a uniform gap, whereas this is not necessarily the case in graphene on HBN, for example, where there's going to be a lattice mismatch and a moire pattern formed where the sign and position and strength of the gap will vary throughout the system. So you're going to see this non-local, non-uniform distribution of mass. So the experiments are very nice and they're showing something, but it's a complicated system with a few different things happening. So it's hard to necessarily assign what you're seeing to maybe a simple valley effect. So what we would like to do to further explore kind of valley dependence in this type of system with a mass is essentially to take the basic idea, but replace the valley splitting mechanism with something that allows us to reconcile the theory and the experiment. So a type of system that typically it is possible to look at in quantum transport simulations. So we would be able to trace it through to experiment or suggest different types of experiments to confirm a valley dependence. So is there something we can replace this Berry curvature dependence splitting with another mechanism? And the solution that we tried, rather than having a uniform mass term throughout the system, was to embed finite regions with a mass. so that most of our system is going to be ungapped. We have no global gap. It's bare bones graphene, but we will have regions then with a gap in it. And what we were hoping is that scattering from these regions would lead to a valley splitting, which could then give rise to an overall effect. So to investigate this, we started by asking, how do electrons scatter from these types of regions? So we attacked this from a few different perspectives. The first was an analytic scattering problem. Simply, if we have an incoming wave, a scatterer, and an outgoing wave, how do we relate them? This is essentially a reformulation of the barrier problem in polar coordinates. So to solve this, we typically write the wave functions in each part in terms of angular momentum basis sets, Bessel functions, Hankel functions, that type of thing, and solve each mode separately and then add them back together for the total picture. This is an approach that's been applied for many systems in graphene. In this quite nice paper, they looked at a potential dot rather than the mass dot we're interested in, and they find nice lensing effects and so on. But back to our system, it's very similar, except in our dot region, we now have a sublattice dependence in some of our coefficients. Otherwise, we follow a quite similar approach. So we use boundary conditions. We essentially force continuity at the edge of the dot and find the scattered and transmitted coefficients for each mode. There's a few symmetries in the system we can take advantage of, and these allow us to relate the K and K prime valley solutions and also to make predictions about the symmetry of the system. This tau is our valley index. We can also calculate the currents for each valley to compare how the electrons in each valley flow around the dots or scatter from the dots differently. So one important symmetry we noted when we looked at the scattering coefficients in this system was that every mode in the K valley had a corresponding mode with the same coefficient in the K prime valley, but with the opposite angular momentum. So these coefficients were kind of equal in different valleys, but for opposite angular momentum. This allowed us to relate, for example, how the angular and radial component of currents would vary. But the key message here is that the angular behavior around these dots is swapped for different valleys. It essentially is also, you can view this as a symmetry, an anti-symmetry around the x-axis or in the y direction. So if an electron in the K prime valley flows in a counterclockwise direction around the dot, around the edge of the dot, an electron from the K valley will flow in a clockwise direction around the top of the dot. K prime electrons in this case are scattered widely to the top, K electrons are scattered downwards, and so on. So this is a symmetry that just comes out analytically from looking at the structure of the individual angular momentum modes. We can also see, for example, if we look at the total current, the valley polarization of this near the dot. So the total current flowing around the dot looks something like this, and we see that there's up here a flow of K prime current being scattered, and here a flow of K current being scattered below the dot. So this does induce a valley splitting, somewhat similar to what we saw in bubble structures. This splitting also has an energy dependence. And the interesting thing here is, although the strength varies somewhat, so it's much stronger in one region than another, this is an overall measure of the valley asymmetry. We see that it sticks to the same sign. So the strength will vary a bit, but the sign stays the same. And if we look at these regions, we see what's essentially happening here is we move from a strong transverse scattering. So K electrons were going down, K prime electrons scattering up. As we shift up in energy, we have the same anti-symmetry around the x-axis, but scattering is in a more forward direction and less pronounced. So there's less electrons being widely scattered, but they still are scattered asymmetrically around the x-axis. Something we also saw, that as well as the overall scattering direction being quite robust, the effect didn't seem to depend hugely on the composition of the dot. So we were able to compare the analytic flow of current with a full tight binding simulation of current flow. And first of all, we found is that for example, the analytic Dirac model agreed quite well with a tight binding model. So we could confirm that this analytic picture would be valid for a reasonable sized dot, rather than kind of the scale-free Dirac approach. But also if we use the disordered dot, so rather than having a uniform mass term everywhere, if we had 10 times the mass, but only on 1/10 of the sites, so that we kind of kept the average mass the same, we would see a very similar scattering pattern, a very similar valley dependence to the scattering, which was nice, as this suggests maybe some of the sublattice dependent doping mechanisms would also be a way to explore these systems. So the valley splitting was not dependent on the exact dot composition. So here's a valley scattering mechanism. Will it give rise to some of the same effects and some of the same measurables as we discussed earlier? So we performed Kubo-Baston simulations to look at the valley Hall conductivity. In this case, we're going to have a periodic system of dots, and by changing essentially the size of the supercell here, we are changing the separation of these dots. And we see, quite like the uniform case, which is shown here in gray, we see a peak in the valley Hall conductivity. So this individual scattering mechanism we show at individual dots gives rise to an overall material property when the system is tiled. So the peaks are in the same place, but the height of the peak depends on the dot density, suggesting it's not a quantized effect. It's not an intrinsic effect like the uniform case was. There's something else at play here, something different. So when we look at the Fermi surface contribution, if you remember previously, the uniform dot case depended on Fermi C contribution, so that if you look at the uniform case and look at the Fermi surface contribution, this is a simulation parameter, but if you go, as you take the asymptotic limit, the Fermi surface contribution vanishes for a uniform mass term. So it's all driven by the Fermi C, whereas for the case of different dot systems, the Fermi surface contribution was saturating at finite values, suggesting that there's a Fermi surface contribution to the valley Hall conductivity, which means it's something that will be consistent with measurements with, for example, or simulations with Landau-Buttaker methods, which belong entirely at the Fermi surface. So it's something that if it shows up in experiment, it should also show up in your quantum transport simulations. So we decided to simulate some systems. So we got maybe what could be an example device, a Hall bar, similar to what was used in the non-local experiments mentioned earlier, placed some of our mass dots in it, and then looked at finding what was happening in the system, directly calculating the non-local resistance that you would see here. So in this case, what we do is we're applying a current between two sets of probes, measuring the voltage between two others. It's a direct non-local resistance measurement. So what typically do we get from these? Well, the first result I'm going to show is without any dots at all, just to give you an idea of what the system looks like. And because this is a finite system at 0K, there's a lot of finite size effects. There's a lot of these oscillations which look pretty messy. And these are coming from oscillations due to the size of the dots, the size of the system, the size of the gap between them, and so on. The important thing about these is that they're oscillating around zero. They're probably not going to show up in real experimental conditions, and they will tend to average each other out. However, if we introduce mass dots, we see a different picture. We no longer have this curve that's averaging around zero. We get a shift. we get a peak type feature here. That's definitely positive, but positive non-local resistance for energies within the gap of the system. So we're seeing a definite change in the behavior and the formation of a non-local resistance signal. The important thing to point out is that this behavior is not just something that was caused by introducing any scatterer. If we replace these with potential dots, so restore sublattice symmetry but have scattering behavior, we see we return to something again that oscillates very quickly around zero and tends to average itself out quite quickly. So this boosting, this kind of robust boosting of the non-local signal is indeed seems to be connected to breaking sublattice symmetry. The other thing that we can do is we can directly map the current flow in these systems, and from this extract the valley dependence of the current flow. So in this case, again, we're looking at driving current here, and we have measurement probes over here. And with mass dots, we see a few interesting features. First of all, we see this strong valley splitting at individual dots, as predicted from the single dot picture. The other thing we see is that the non-local signals, the current away from the direct path between source and drain, is largely valley polarized. So this color code here is showing the valley polarization. You can see all the current flow over here is quite strongly valley polarized. And this valley polarization, a valley polarized current mediated or traveling throughout the device, is consistent as we kind of vary the parameters of the simulations. If we move the dots around a bit, or vary the device size, or vary the energy, these systems have a lot of finite size effects, so the exact position of the various vortices and currents changes, but the key qualitative features, a boosting, for example, of currents near the edge, a strong valley polarization, and a general boosting of non-local resistance, we find independent of these, and independent, for example, of the edge geometry, suggesting that this is a mechanism that can perhaps give rise to something that could be measured in experiment, and something that could be traced back to a valley mechanism. So this result is published in this paper, which is published last year. I think moving forward on mass systems, we have shown that there's an extrinsic scattering-based valley splitting mechanism that can arise, which should give rise to valley Hall effects, whose signatures then can be directly simulated and compared with experiment, that there's kind of a consistent connection between the underlying mechanism, between transport simulations, and between transport measurements. It's kind of, you can directly compare each stage and check for consistency. However, there are a few issues. Engineering mass in graphene is difficult. It depends on tuning things at a sublattice scale. If you tune substrates using, for example, HBN, the lattice mismatch is going to give rise to moire features, and these will be difficult to account for, because as well as having just, for example, the mass dot, you'll have a variation, you'll have changing signs, snake state type things forming, and so on. So it's a more complicated system. So it's going to be hard to model exactly and hard to account for, example, local strains forming, things like that. Doping is also maybe an interesting way forward, but apart from these few experiments a few years ago showing the formation of these domains, there, as far as I'm aware, there haven't been any transport measurements. So making the kind of device we require to show this would be quite difficult. So how do we go on towards maybe actually looking at more realistic experimental systems where these type of effects might be visible? And the key is to move from monolayer to bilayer graphene. So in particular, moving to Bernal stacked, so the most common type of bilayer graphene, it's gapless, but a gap can be induced here not by breaking sublattice symmetry, but by breaking layer symmetry. And this can be achieved easily enough by dual gating, having a top gate and a bottom gate. You can tune the potential of the top layer and the bottom layer separately and induce a gap. So our question was, can we exploit this to direct valley currents or to split valley currents in the same way as we thought was possible for monolayer graphene. And we're inspired here by a whole range of similar experiments that suggest there may be a valley-dependent Berry curvature, so a few theory results, and signatures showing non-local peaks associated with this possible mechanism or with valley mechanisms in experiments. So what we're looking for is this key ingredient. If we have a local dot with a gap induced by a bias, will we also see a splitting of the valleys? And again, because layers are easier to control than sublattices, the type of system we're suggesting are already being looked at in experiment. So the potential and mass profiles in bilayer graphene are easily controlled, and the setup's already in use, although the motivation is often somewhat different. They're looking at creating kind of isolated quantum dots and looking at the confined states in those dots and maybe trying to create qubits or so on by confining states and applying magnetic fields to break various degeneracies. But the basic setup is the same. So we looked at scattering in these systems and to see could we achieve valley splitting using scattering from such dots in a bilayer device. And indeed, we can. So if you look at how electrons scatter from such systems, there's again a strong valley splitting. In this case, K electrons being scattered upwards, K prime electrons being scattered down, something that's visible here in the current flow for the K valley. You see this flow towards the top of the panel here of K valley electrons. So we see a valley splitting, and there's a few differences from monolayer graphene. And in general, what we found was that the energy dependence in bilayer graphene was smaller. There was some variance in angle as you change the energy or the exact parameterization, but it was smaller, suggesting perhaps a more robust or at least a more consistent mechanism as if some of the parameters were varied. So the energy dependence is shown here, and you see that throughout much of the gap, the valley dependent scattering is somewhat similar, and also the angular dependence throughout this gap region here. There's not a big change in the angle. It's about, in this case, it's 30 degrees and minus 30 degrees for the two valleys. So the similar behavior over a wider range of energies, which again might be useful for trying to confirm this setup. So this work was also published last year. Something that is interesting is that this valley splitting with kind of streams or jets at plus and minus 30, this has actually been seen in an experiment, not with the setup exactly that we suggest, but with a gate-defined channels. And if you look at the spreading of current beyond this channel, so in this region, they find these streams or jets separated by about 60 degrees, and which when they do their theory, they expect these again to be due to valley polarization. The interesting thing here is that their mechanism is very different to ours. The key mechanism that they have for this valley splitting is a band structure effect, essentially trigonal warping that's induced by higher order hopping terms in their Hamiltonian. So interlayer hoppings, but between atoms more distant from each other, gives rise to a warping of the band structure, which creates a different effect for K and K prime electrons. However, we can rule out this mechanism in our model simply because we don't include those terms. So the effect we see in our model is not a band structure effect, it's a scattering effect from these dots. But it does maybe raise some interesting questions about future studies, about maybe the competition between these two effects, whether it'll be additive or whether they'll tend to cancel out. So it's an interesting, I think, thing to look at moving forward, and something we haven't done yet. Okay, so if you're interested in reading more about valleytronics and graphene in general, and these kind of ideas about scattering versus Berry curvature effects, Fermi surface versus Fermi sea, topological versus trivial, valley dependent versus non-valley dependent, There's a nice article in Physics World last year that talks about these. And also we had an overview in Journal of Physics Materials that came out in January this year that talks about these types of effects, how to interpret experiments, particularly non-local resistance experiments, if there are possible underlying valley effects, or kind of maybe how to move forward or how to design new experiments to detect these. Okay, I'm going to change course dramatically now. How am I doing for time, Thomas?
We have about 15 minutes.
Okay, I probably won't get both of these done, but I'll go through the first one. Anyway, so I'm going to move on and leave valleys behind completely and talk about edge magnetism in graphene. So the theory here is that zigzag edge states in graphene, as shown here and here, behave very different to, for example, armchair edge states. Zigzag edge states break sublattice symmetry locally. Every exposed atom along this edge belongs to one sublattice, and every exposed atom along this edge belongs to the opposite sublattice. This gives rise to localized states, which will give rise to a very this flat band here, or a peak in the local density of states. This peak, strong peak in the local density of states, if you consider a Stoner argument or can include electron-electron interactions, it's spin splitting, or it's predicted to. So you get a splitting of this and magnetic moments at the top and the bottom edge, as shown here. So this idea of spin polarized edge states in zigzag graphene systems has led to a whole range of suggestions or proposals for spintronic devices. So the main obstacle to overcome usually is to break the symmetry between the edges. That essentially, yeah, we have a spin up edge and a spin down edge, but if we drive a current through these, whatever happens here is going to be compensated by something happening here, and we have no net spin signal. So there have been a few suggestions. Perhaps the most famous one is to apply a transverse electric field, which will break the symmetry between the sides and can lead to half metallic behavior. Another approach, maybe more dramatic in breaking the symmetry, is to take a big chunk out of one edge, breaking the spin current at one side so that you only have spin current at the other. And this could be used maybe as a spin injection mechanism, that if you only have current at one edge and that's spin polarized, you're only going to inject electrons of that spin type. And there's a wide design space for playing around with zigzag edge structures. So you can consider, for example, dots, and as shown here, and looking at how the spin changes depending on as you add or remove electrons from the system. There have been a large number of suggestions about various ribbon geometries, ribbon devices, combining zigzag edge segments with other types of edges, ribbons of various widths and so on to get different behaviors. And something we've looked at is the opposite of this, to look at essentially subtractive dots. If we remove graphene from a sheet, but leave behind zigzag edges, or in this case, triangular systems, can we see interesting behavior? And something we looked at was something kind of analogous to the valley-dependent scattering I've been talking about to date, but spin-dependent, looking at how spin would scatter from these type of systems and these type of devices. The important thing in all of these is that there is a strong sublattice dependence, that if both sublattices are the same, the moments will be the same. If sublattices are opposite, the moments will have opposite orientation. So triangles are quite nice here, because you can make a triangle where all the edges have the same orientation, so you could have a net spin. In experiment, a lot of the kind of ideas I'm talking about now have been around a while, but they took a long time to be confirmed, because making zigzag ribbons or graphene systems with these perfect edges was quite difficult. But now there are methods, kind of etching methods, that can control the edges or get the edges to reconstruct to how you want. or different growth mechanisms. And this really has been spurred by the huge potential of bottom-up techniques, where a kind of very, very exact edge profiles, designer ribbons can be constructed. Or, for example, epitaxial ribbons grown on silicon carbide. Depending on how you prepare the surface, you can get ribbons with very nice zigzag edges. So some of these structures that are suggested for the spintronic applications are now possible. With this in mind, a lot of the experimental approaches towards detecting these types of edges are a little bit indirect. And the key here is that spin polarized edges will have a different electronic signals to non-spin polarized edges. So you'll see a different behavior, for example, of the size of a gap versus the width of a ribbon, or which is often the main one used, or you'll see different changes in the local density of states as measured, for example, by STM. So if you have spin polarized edges, you will expect to see a gap form. You'll expect to see maybe high density of states in certain regions. Or you will expect, if you know the width of the ribbon, if it's spin polarized, you would expect a certain gap size, and so on. But the key thing here is that all these proofs, if you like, of spin polarized edges kind of depend on you knowing what should happen. And this typically means you compare with theory. You do a simulation of ribbons with or without spin polarization and try to compare to see what's going to happen. What should the edge state look like if it's spin polarized? Do I see that if I look at it with an STM? That's the basic mechanism that's used. So this approach actually, this reliance on comparison with simulation raises some interesting issues. Essentially, how do you find, how are moment profiles found? How do I know if I have this type where the spin up and spin down moments are and what size they are? So typically you either use a spin polarized DFT calculation, which is limited to very small systems as it's very expensive, or you do a self-consistent Hubbard solution. So you use a tight binding model, you add a Hubbard U, and you do a self-consistent procedure to find the correct moments. This, although much lighter than DFT, is still reasonably heavy by tight binding standards, and you typically tend to be limited to systems with approximately 1,000 atoms. So this makes it difficult to investigate a range of relevant systems. So for example, large networks of bottom-up nanoribbons, which might be clean locally, but will meet each other at different angles and have different types of edges, and so on. Or to look at the interplay between these magnetic edge channels, transport channels at the edges of ribbons in the presence of disorder, where you typically need to look at large numbers of configurations to see what's going on. Also, it's hard to know what will be the localized states in a very large nanoflake like this. So if you've made a system an experiment and you want to see are the edges polarized, and you essentially need to know what the electronic structure will be. And if it's a large system, that will be difficult to calculate. However, many of the key features are pretty intuitive. We can see that we tend to have large zigzag moments, large moments at the center of the zigzag stretches. The moments are much smaller along large, long armchair edges or near corners, or as we go into the bulk of the system. So there are some obvious trends, but it's not easy or quick to actually find the numbers that you need for the simulation. And the quantities that you want to calculate depend quite sensitively on having those numbers correct. So we decided to look at other approaches to solving this problem. And essentially, machine learning, and in particular deep neural networks, can be used to approximate mappings between an input and an output if the functional form of this mapping is unknown or it's difficult to calculate. So in our case, we took that the input to our neural network would be geometrical information about, for example, a graphene nanoflake with a random edge profile, where we knew the type of edge of each atom. And our output would be, for example, the moment at that site. So we will give, for example, if we want to know the moment of this site, we will give how far are we from important edge sites? And we wanted to learn then, okay, your moment is 0.2 Bohr magnetons or whatever. So does this work? So we decided to test it. We generated a library with thousands of random edge graphene flakes, things like this. And we played around with designing a good descriptor that contained, kind of using a little bit of physical insight, contained the information about different types of edges of various types, sublattices, dependencies, lattice connectivity, and so on, and built a geometric descriptor based on this. And then trained this using pretty standard methods to try and map the descriptor, describing where each site was, to the magnitude of the moment, to try and, if you want, learn the trends that we discussed earlier, but that maybe are difficult to put into an algorithm, a direct algorithmic form. We then, of course, would test this result on a wide set of unseen systems similar to our training geometries. And the accuracy we got out is quite good. So if you're not used to looking at these type of calculations, essentially if you plot actual versus predicted, you're hoping to see something strongly centered along the diagonal. And that's what we find. We get a good agreement between the predicted moments and those from full self-consistent calculations. A general trend we find is that the network is more accurate for larger systems overall, but this is to do again with the breakdown of how many atoms are at the edge and have large moments and how many are in the bulk and have quite small moments. And generally this is fine because small systems are easy to calculate self-consistency. It's the large atoms we want to be more accurate on, and this is what our system tends to give us. We can also analyze the performance of a network by site type, and we see that we're good not just for example, zigzag edges, where the widest variety of moments are, but also for edges in the bulk or at the other different types of edge. So although they're most associated with zigzag edges, moments can also occur at armchairs or at this third type that we define. So nicely, our system also worked very nicely on unseen systems. So this is an example of an unseen flake in our library. And you can compare the actual moments from a self-consistent calculation with those that are directly output by the neural network. There's an error map here that shows you exactly where there are slight errors, but the magnitudes of these are small. Again, shown here by plotting the actual versus the predicted. You can see that everything follows this line of equality, as you would expect. Importantly, not only are the moments correct, but important quantities that we calculate from them are correct. So if we look at the energy levels of this flake done with a full self-consistent moments or the machine learning predictions, they're almost identical. So we can extract important quantities using machine learning and they will compare well with a full calculation of the moments. So the important thing here is that our approach here learns moments on a site-by-site basis. So each site is predicted individually. It doesn't have an idea of the overall structure of the flake, which means it can be applied easily to systems of arbitrary size. Our descriptor won't only work for small systems or big systems, it will work independently of size. But despite not knowing about the global properties of the flake, it's able to, if we use the moments that we guess, we're able to accurately calculate global properties. So for example, the homolumo gap of all these flakes, we get a very good estimate here above a certain threshold, of course. And also something perhaps more interesting is that bipartite systems like graphene obey Lieb's theorem, which is that the total magnetization should be equal to the sublattice imbalance due to the importance of sublattice. This is something that our machine learning system hasn't been told. It doesn't know how many A sites or B sites are in the system, but yet the total moment, when you add together the results of the individual flakes, follows this very, very closely. So what we've built maybe to be useful to the community, and which hopefully will be released soon, is a tool so that people can actually play with this and use this in their own study. So rather than having to do this self-consistent procedure, if you're looking at magnetic systems, we've built a package that will allow you to load in particular geometries, which might be interesting if you're doing experiments in these systems, which will assign the different edge types and predict moments. And if you have small enough systems or a strong and big enough computer, you can also compare these directly with self-consistent calculations. So this allows us to do, for example, very big systems that we would be unable to do by hand. So in this case, if you had a patriotic Mexican graphene flake, you could very easily predict its moments. And I see there's some nice zigzag segments along the peninsulas and on the coastline. Whoops. So I'll finish with a very quick discussion of an application of this. Something we were looking at was the effect of edge disorder in zigzag nanoribbons on transport properties, something that's maybe easy to look at a small scale, but difficult to look at a large scale thoroughly, because you need to look at, for example, if you're looking at smooth edge disorder, long range disorder, you need big systems, and you need many big systems in order to do configurational averaging. And these are very difficult. You need systems with tens of thousands of atoms, which are difficult to do self-consistently. So we can use machine learning moments instead. So what we can do, for example, is pick a small system that's even still at the upper limit of what we can do self-consistently, and use this to benchmark our results. So we see here that the transmission for both spins, that's up and down, and for both methods, both self-consistent, shown here as dots, and for the machine learned moments, shown here as full lines, agree extremely well. So you can use these instead of the self-consistent moments when you're doing transport calculations in this regime, and you should get pretty accurate responses. This allows you then to scale up, that you're confident it'll work, and you can go to much larger systems that aren't possible with self-consistent techniques. And you can look at the interesting effects that arise there. You can also, for example, visualize the spin-dependent current flow and see that in some of the cases we looked at, that a spin polarized channel at the edges, which is kind of the necessary ingredient for many proposed spintronic devices, indeed persists in the presence of long-range disorder, something that wasn't possible to look at before. So we see this nice effect from pristine ribbons persists with reasonable levels of smooth edge disorder, but in a narrower energy window. So this, of course, can have effects for designing these devices and testing them and so on. So I'm going to leave it there. I'm not going to talk about the final section. I think it's getting a bit late, but I'd just like to thank the collaborators. Like the collaborators on the projects I've spoken about, Mikkel, who worked on the strain stuff, particularly Thomas and Jose, who worked with us on the mass terms in monolayer graphene, Fanula, an excellent undergraduate student who looked at the bilayer graphene mass terms, Merch and Sean, who worked on the zigzag edge magnetism, and Zara, who worked on the spin orbit stuff, which I didn't get around to today. And thank you for your attention, and I'm happy to take any questions you might have.
Yeah, thank you very much, Stephen, for this wonderful, very interesting talk. I enjoyed it very much. So are there questions, comments from the audience? Eduardo, go ahead.
Thank you, Thomas. Thank you, Stephen. A really, really nice and really clear talk. Wow, it's really good.
Thank you.
So I have two questions, and one is related to something really specific in this machine learning approach. So
sure.
When you mentioned that you compare with the self-consistent calculation, what do you mean? It's a Hubbard model?
This is a Hubbard model, yeah. So it's a mean field approximation to the Hubbard model. So there are a number of other studies that do look at using machine learning together with the Hubbard model. We're a little bit different here. The other studies in this area have tended to focus on exact solutions to very small systems. Whereas what we've tried to do is focus on maybe what's more relevant to what people are doing in material science, which tends to be a mean field approach to the Hubbard, but on much kind of larger nanoscale, but heading towards mesoscopic scale systems. So systems that would be relevant to quantum transport, quantum dots, that type of thing. So the simulation approach there tends to be either DFT for very small or perfectly pristine or periodic systems, or failing that, some variant on the mean field approach to solving the Hubbard model. So this is a self-consistent approach I mentioned. So typically you guess a moment profile, you use this to calculate the density of states. This gives you a new guess for the moment, and you solve until converged. So for each of our systems, we essentially did that. We found the moment profile and then trained the machine learning to return that.
Okay, and just for curiosity, for example, in the case of the Mexico country map, so then how do you compare the times between the prediction that you can make?
Okay, so for the Mexico example, that's a big system that's only machine learning. But for example, the other systems I've shown and some I didn't show, we have a range of what I would call intermediate systems. So this example here, the machine learning wasn't trained on this system. It's in the test set, but it's of similar scale. It's a bit smaller than the Mexico example, but it contains all the same features. So I haven't shown it here. It's in our, there should be a preprint out next week, hopefully. We're in a kind of a reformatting war with the journal, but we show some examples there of systems which are a little bit different. So the systems that we're trained on here are all finite flakes, but for example, I don't show it here. The moments here in this system, this is sort of a reasonable sized nanoribbon system. These we did both self-consistently and using the machine learning, but this system was quite different to the flakes in our system. And also we looked at, for example, testing it on anti-dot systems. So we didn't train the network on anti-dot systems. It doesn't necessarily know an internal edge from an external edge, but it also predicts those moments correctly. These kind of fiddlier systems depend quite strongly on exactly how you build the descriptor. So it knows how far away you are from an edge, but it's not a Cartesian distance. You need to account for some of the peculiarities. We know edge magnetism in graphene depends on the location of nearby edges. We know it depends on sublattice also. So we kind of need to build that into the descriptor. But once you're a little bit clever with that descriptor, it's generally able to learn quite quickly the essential trends, and then you can fine tune it to catch more.
Okay, thank you. Can I make another question?
Go ahead, Eduardo.
Yeah, it's related to the valley splitting and the bilayer system. So when you will show this image of the valley splitting, are you average with the two layers, the contribution of the two layers, or it's just one layer in this figure?
It's both layers. The bilayer systems this is entirely a Dirac continuum model approach, but it's
okay.
From that perspective, what I would say is that it's a 4-band rather than a 2-band model, which I think would be a little bit more robust, and you're including both sublattices on both layers in that model. But the valley analysis there is reasonably straightforward. We haven't broken it down beyond that. We looked a little bit, but it wasn't that interesting in breaking down further into valley on layer 1, valley on layer 2. That's, I think, maybe an interesting place to go in the future to look at the coupling between valley and layer. And I think some people have perhaps looked at that. I think it would require more complex mass engineering. I'm not sure if the single dot is necessarily the best place to see that type of effect. A system we did look at, and which does show that type of behavior, and it's in the same paper, we looked at a bilayer dot embedded into monolayer graphene. And so if you want the system outside the dot, if you want out here, is monolayer, and the dot itself is bilayer. Because we're using a Dirac model, we have to be slightly artificial here because the boundary conditions are different for zigzag and armchair, and you can't have a circular dot that's entirely zigzag. But once you make some approximations, we still see a strong valley splitting effect. There's a kind of a slightly nonsensical edge dependence. So we look at a few different types of edges, and the common behavior we say is the important trend there. And that system within the bilayer region shows some interesting layer dependence. I don't think that there is a breakdown because you're changing the potentials on each layer, so you are choosing an energy, and it's not going to be symmetric, but it's not something we analyze in a huge amount of detail. I think it would be interesting to look at this maybe further in that point of view, using layer as the degree of freedom rather than valley. But you will have some. The layers are the Hamiltonian for bilayer graphene entangles the layers anyway. So.
Okay. Well, thank you.
Okay. Yeah. Are there further comments, questions? Okay, I have some, Stephen. When you go to the next slide, regarding the question which already made Eduardo, in this density figure of the current flow, I see there that the current flow is somehow asymmetric with respect to the horizontal line in y equal to 0.
Yes.
Do you have an idea where this asymmetry comes from?
This is exactly the same effect we mentioned in monolayer graphene, that essentially you only get the full symmetry when you consider both valleys together. So this current flow is only the current flow
it's only from K
of the K valley. Yeah, you are right. This, you would expect when you add both together, the K prime situation is the exact swap, similar to what you
see in the figure on the left.
Exactly as shown here.
Okay, I see. Thank you for clarifying this. And next question. You showed us this Valley Hall effect, which is caused by this distribution of mass regions, right? So you have this exactly. Yeah. So you have this distribution of mass regions. Do I understand correctly that you, or have you tried to obtain similar results, not by using mass regions, but by using just these bumps, where all these pseudomagnetic valley electronic started? So instead of placing their mass regions, just Gaussian bumps or something like this. Would this cause also?
I would expect so. It's something that I started doing, but focus on the mass regions. The calculations are, I think, set up, and possibly there were some samples done. I think the effect is going to be quite similar. There's going to be a transition from individual scattering to a Valley Hall effect, which one then might give rise to another. But I think perhaps, if I'm not mistaken, Eduardo, maybe were you on this paper with Mikkel or was it Jose, who looked at this Valley Hall? It wasn't a device setup, but it was a periodic system. Were you involved with that work?
No, in that work, no. Okay,
but I know that Mikkel and Stefan, a few years ago, they have a 2D materials that it was looking at the Kubo-Baston side of things with a periodic array of bubbles. And their interesting feature from a pseudomagnetic point of view was the combination of a pseudomagnetic field and a real magnetic field, and they tuned the real magnetic field to exactly cancel the pseudomagnetic field in one valley, so that you would have double the Hall effect in one and none in the other. And they had some nice results in that system. But again, it wasn't in a transport geometry. One thing I'll say is while this type of simulation is reasonably quick, the current flow mapping, and particularly the valley polarization here, which is gotten from the spectral function, is a bit of a nightmare, kind of computational wise and memory wise. So you kind of need to kind of pick a very specific energy and wait kind of quite a long time to get this picture out. I think there's probably a faster way of doing it than what I have done, but it works. So I think there may be some interesting work and possibly in future. As I said, we kind of moved on a bit from bubbles because I wasn't sure experiment was catching up quickly enough. But these types of systems with designer bubbles in particular arrays, with the expected, for example, this breakdown, this six-fold symmetry in pseudomagnetic field, this paper, I think in particular, sees that variation in pseudomagnetic field. If they look at their Landau levels and how they vary spatially, they see this six-fold structure. So all the ingredients that you need, I think, are now there in experiment. You can make these bubble structures. They have the required strain profile, which is supported by STM measurements of local peaks. And you can place them where you want. You can control their height. I mean, this is really cool. This is, I think, it's graphene on a hydrogenated germanium surface. And when they tap it with the AFM tips, they can selectively dehydrogenate some of the germanium, and this then inflates the bubble. And depending on how hard they hit it or the voltage they use, they can control the height, the radius, and all these things. So it's a really nice designer graphene bubble system that they have there, and which I think might be nice. I think some of these studies, I know that I think Sandler Group and Lache as well have looked at larger extended folds, which are kind of a very nice potential valley waveguide system, because rather than kind of having just a closed structure, you have something extended with quite a nice pseudomagnetic field profile. So it's almost like a pseudomagnetic waveguide. I think Peters has looked at this as well, and there are a few very nice papers on this in the last year or two, which I haven't included here. I need to update my slide a little bit, but I think maybe from strain perspective, I think maybe these in the short term, these extended folds are probably one of the more exciting directions, purely because that they're kind of extended, and you can make devices with a few folds where you may expect to see the structure. So you could do the type of analysis that has been done with maybe grain boundaries in the past, that you can have folds that extend or that meet each other and maybe see valley effects there.
I see.
For local structures, I think that the bilayer dots, I think, are probably the best small valley scattering mechanism. So out of bubbles, monolayer, mass, or bilayer, I would say the bilayer, the biased bilayer dot is the most accessible and maybe the most interesting.
I see. Okay, thank you very much. Are there further questions, comments from the audience? If this is not the case, I have another question. In your opinion, you showed us this machine learning approach for these spin polarization at zigzag edges of graphene flakes. Would it also be possible to use this machine learning for calculations of the current flow in much larger graphene devices. You know, when we take just a tight binding model without some self-consistency, with tight binding, we can go to 1-2 million of atoms, 5 million of atoms easily, but there are also some limitations, and it would be nice to go to, let's say, devices which have micrometer size as they are used in the experiments.
Yeah,
and
I think you'd be kind of probably moving away from the need for full quantum simulations. Then this is an interesting point, and it's it's something we've talked about. There are papers that look at directly predicting transport properties. Something of the reason we haven't, well, it's something we have looked at. It's an unpublished work. The usefulness of that, because a lot of transport properties, you can use a recursive method. You can break the system into small cells. You can do this quite efficiently. The system needs to be incredibly big before you can't break it apart in a clever way and use parallel computing and get it to work quite well. Like in our application here, the this study of transport in nanoribbons, we're not using machine learning to predict the transport. We're using it to predict the moments and then using those moments in the transport calculation. And the key here is that it's the moment prediction by a huge margin is the bottleneck.
Yep.
If you're doing transport simulations, so these are done, I think, in TB-trans, but if you're using TB-trans quant or even your own code, if you have a reasonably efficient recursive Green's function method built in, if you split up the cells cleverly, and you have a system with this type of aspect ratio, very long systems, which tends to be the nanoribbon setup, you can go pretty big. Using existing methods, there's not really the same need to use it there. I think it's interesting to see in its own right, not so much as from an application perspective, but to see, maybe to get some insight if there's maybe a simpler description can be used, if there are patterns or if there are trends that maybe aren't intuitive to us, that maybe suggests something about how transport is behaving. But maybe there's more approaches by stepping back and guessing on a structural rather than an atomistic level, or in heterostructures, looking at maybe combining the layers of a stacked heterostructure, or making even lateral heterostructures by having maybe different size features in different places. And there are a few, I think, studies looking at strained systems. I think in particular there are a few machine learning studies there that are quite interesting. But I think with transport for its own sake, or as an alternative method for getting transport, I'm not totally convinced on. I think it's interesting to see how it works, and to get some insights into the type of descriptor needed to get a good result. But whereas I think the result we've shown here is interesting and allows you to go larger than is possible conventionally while keeping roughly the same accuracy, I think that's maybe useful. And I think the direction we will go down in the immediate future is kind of maybe fine-tuning this to work in slightly different situations, for different doping levels, in the presence of other types of impurities, vacancies, maybe even other materials, or rather than playing with the material side, playing with the model side, moving away from the simplest mean field description to maybe a mean field description with non-local terms. See what kind of descriptor engineering you would need to capture those effects and so on. So I think that's maybe a more interesting direction to go in next here.
I see. Okay, yeah. Thank you very much. Are there further comments, questions? Yes, Stephen?
Oh no, I was just thanking you again.
Okay. Okay, yeah. If there are no further comments, questions, yeah, thank you again for joining us today, for working late night I think in Dublin it's now almost 9 o'clock. And so, yeah, see you next week. Bye-bye.
Great. Thanks, everybody. Bye.
Bye-bye.